Okay, so far we have worked with geometric series, and we know how to tell if they converge or if they diverge. We know that if the radius is in between -1 and +1, that our geometric series will converge. But what happens if we don't have a geometric series? So that's when we have different tests that we can use to determine convergence or divergence of series that are not geometric. And the first one we're going to look at is the integral test. On this slide is the definition or the explanation of the integral test. And it just says let a sub n be a sequence of positive terms. And suppose that a sub n is some function where f is a continuous, positive, decreasing function of x for all x's in the domain. Then the series and the corresponding integral shown both converge or both diverge. And all that says is if you have a series like this one here, one way to test for convergence is to take this a sub n and write it as a function of x and then integrate it. Now this becomes an improper integral, which we know how to evaluate. So we do that by changing it into a limit and then evaluate from there. This slide just kind of shows you geometrically what's going on. Here is a series. It is continuous. It's positive because it's above the x-axis, and it's always decreasing. So if that's the case, we find the area underneath the curve. And if this area is finite, in other words, if we get an answer for our integral or for the area, then our integral converges, and so does our series. All right, on this next slide, we're going to actually do an example of the integral test. We're going to look at this series right here, n equal 1 to infinity of n over n squared plus 1. So our sequence is right here, and we're going to change that into a function of x. We're going to take that function of x, and we are going to integrate it. Now, I did not go through all the steps of integration here, but this step right here is just showing that I multiplied the top by 2 and the outside by 1/2. I was just setting up u substitution. So at this point, you should probably turn off this recording and see if you can integrate this integral right here by changing it into a limit of an integral and then getting right to this point here. The limit as b approaches infinity of the natural log of x squared plus 1 evaluated from 1 to b. Once you get there, then we need to stick b and 1 into this function and evaluate it. So here is our limit. We just stuck b into the function. Then we subtracted what we got when we plugged 1 into the function. Well, the natural log function is an increasing function, so it grows without bound. So in other words, this limit right here, as b gets large, will be infinity. So this integral does not converge. It is a divergent integral. So since the integral diverges, then the series also diverges. Here is another example, close to the first one. We're looking at this series right here, from 1 to infinity of 1 over n squared plus 1. Here is our sequence, and we're going to switch that into a function of x. Then we are going to integrate this function of x between 1 and infinity, just like the series was, from 1 to infinity. Hopefully you all know that this is a flashcard integral, and when you integrate this, you get arctan. So now we have a limit as b approaches infinity of this function arctangent. And we're going to evaluate it from 1 to b. If I stick b in here, I get arctangent b, and if I stick 1, I get arctangent 1. We subtract them and take a limit as b approaches infinity. Well, the arctan graph, as b gets large, heads out to pi over 2. And the arctan of 1 is pi over 4. If we subtract them, we get pi over 4. So the integral does converge. It does have a finite area. And so since the improper integral converges, our series converges. That's basically all there is to the integral test. However, we do have some special series called the harmonic series that we can prove convergence or divergence for using the integral test. This right here is called a p-series, and it's the summation of 1 over n raised to some power p. Okay, now we can do an integral test on this. As a matter of fact, I have one, and I'll see if I can throw it up here. But if this exponent here is greater than 1, it converges. And if it's less than 1 or equal to 1, it will diverge every time. So you can either use the integral test every time to determine convergence, or you can have this memorized. A p-series will converge if that exponent is greater than 1, and it will diverge if the exponent is less than or equal to 1. And this is a series that you will see a lot as we move on in this chapter. This right here is called the harmonic series. It's when the exponent is 1. And this is what the harmonic series looks like. If I were to integrate this series, it would be a divergent series. So our harmonic series will always diverge. So I just real quick went to Word and typed this out. If you take this harmonic series, 1 over x, and integrate it from 1 to b as b approaches infinity, we will get the natural log of x, and then we will evaluate that at b and at 1. So here is the plug-in, natural log of b minus natural log of 1. Natural log of 1 is 0, but this natural log function continually grows, and so as b gets large, this will head off to infinity, therefore making that improper integral divergence, therefore proving the harmonic series diverges. Now here are some series, and I think we have enough information now to determine whether they converge or diverge. If you look at this one right here, that would be a p-series with an exponent that is less than 1, which means it's going to be divergent. Over here, this is our harmonic series. The p is 1 on here, and so that is our harmonic, and so it will diverge. Here we have another p-series. The exponent is 1/2, which is smaller than 1, so it also diverges. Over here, another p-series. This 100 here could be taken and written on the outside, and then we would just have 1 over n squared. But it is a p-series with our value of p being greater than 1, so that is a convergent series. Down here, another p-series. The exponent is larger than 1. Pi divided by 3 is a number bigger than 1, so this will converge. And over here, that's a geometric series. And the radius is less than 1, so it will be a convergent series.